Okay, so I'm going to be introducing my work on deep neural networks to analyze deformable shapes from images. I'm Miao Miao from MIA Lab, Medical Image Analysis at the University of Virginia. And I have a group of team, including fantastic PhD students who made this work happen. Deformable shape analysis based on image deformations has been a long-studied research topic in the image analysis and computer vision field. So people have been using the geometric deformations that happened, study along the object, to do analysis, to study the animal or plant growth patterns. And also, most of the time in medical image analysis, the deformable shapes has been used to study disease. For example, Alzheimer's disease. So when researchers try to analyze the group difference between the health subject and the disease subject, and how does the brain actually changes along the different trend or patterns according to the age or the disease progression. So deformable shape analysis play a very important role there. And another very important research I want to highlight that's currently in my group is the image-guided navigation for the CRT to plant the pacemaker. So what we do is that at UVA hospital, we collect the CMR images, and the CMR images, we analyze the motions from the cine sequence. And from the different motions, which is again another very typical examples of the deformable shapes and on how the heart actually beats. So analyzing all this motion and change vectors from the images, then we can understand the difference between the healthy hearts and the diseased hearts. So on the left side, you see the healthy hearts, which on every part of the myocardium, that actually start to contract at the same time. But for the disease, you actually see some of the regions, it's not contracting, but on the other side stretching, which means that's the places where a heart arrhythmia or some other heart disease actually show up. So in our group that we first try to see whether current deep networks can actually understand all these motions. So for those of you who are familiar with image registration work, so all these deformable shape vectors are based on the registration network. So we first investigated that for all of these shape changes, whether this can dramatically contribute to image analysis tasks. The my favorite examples to show all the current deep neural networks, it's not necessary to understand such deformable shapes, is the first example comes from the ICLR paper in 2019 that the team, actually the group, replaced the very local texture of the tabby cat with the Indian elephant. And then you can easily fool the current deep networks to misclassify this tabby cat as an Indian elephant, which is one of the evidence that the current networks actually focus a lot more on the image textures instead of the global shape operators. And another very interesting example is that for most of you who have already known is if you add the adversarial noises in the image space, then you can actually easily fool the classifier to misclassify the object as panda showing in the images as predicted to a wrong gibbon, completely different animals. So all this vision image analysis tasks basically show that the current deep networks does not really understand the global shape information. Instead, they actually bias towards local textures, which is one of the limit or constraint for the deep nets. So we want to understand what if we can teach the deep networks to actually analyze the geometric shapes from images, then will we actually basically, to increase the chance for the neural networks to understand better and also to make mistakes less. The first very initial work we did was trying to derive all these global deformable shapes from images. So for example, if we have a group of images, then we have a reference, which is a template. Then we derive all this geometric shape information parameterized by deformations, and that's through the Atlas building network. And then what we do is that I just flash back to our NeurIPS paper 2022 performed by my student Jian Wang. So we basically, after we learn the deformable shapes for the group of images or within class images, then what we do is that we actually inject the latent shape features and combine with the images. So we fuse these features together with typical classifier. So whatever image classifier that you can name it, it doesn't really depend on any architecture. Then we use this integrate shape and texture features for classification, whether we can improve the classification accuracy. So we have been tested the network on both vision images, which is the synthetic data from the Google Draw and also MNIST dataset. So for all those results that you can check it out in our NeurIPS paper. And we also performed on the medical images, which is the classification tasks on the brain dataset. So we find out that with learned shape information, integrated with the image intensity space, that we can actually substantially increase the classification rate. And another very interesting thing we find out is that integrating the shape features, then we can actually improve the robustness of the image analysis tasks to universal adversarial noises. So this is what we found out. GeoSeek is our method, and baseline is any other current neural networks, the image classifier, with just looking at intensity without actually explicitly understanding the shape factors. So you can see that our method with different level of noise add into the space, that our method is about 10 to 15% more accuracy than the baseline, which means that our algorithm actually more robust than the baselines. So that was a very initial preliminary results. That basically our idea is that with all these learned shape features, can we improve the image analysis task? So another very interesting that we want to look into even further is that, okay, we want to understand the shapes. I mean, how does the object change? But does current deep networks actually understand how exactly the object change from one to the another? So for example, if I give you a pair of images, I have the source image and I have the target image, and then except you tell me how the deformation actually happened between these two objects, whether you can actually tell me the entire changing process. So for those of you, again, who are familiar with registration, that probably you have seen all these softwares, Quicksilver, Deep Flash, Voxelmorph, whatever morph you have. So the current registration network can tell you what's the final deformations to deform from one object to another, but it doesn't tell you the entire evolution process, which means that the current network first meets the deformation metrics, which is geodesics between the object, and also cannot understand the physics of the deformation process. In this way, that I would say the current network is also not able to quantify and to compare the shape differences between two objects, and they cannot analyze it. So we basically, to look at the entire evolution, or mathematically we call this as geodesic, the shortest deformation process between these two objects, that we want to know how exactly one shape that's evolved or deformed to another different shape. So if you see the two examples that I have over here, that with the deep networks, if they can understand how the deformation process actually happens, that you should be able to see the entire, changing process from the source to the target images, no matter what objects you have. So, to introduce how we teach the network to understand this entire process, I would like to go through a little bit background, how to mathematically formulate this entire changing path, or we call geodesic in the deformation process. So this comes back to the very elegant mathematical work for image registration that's called LDDMM. And the algorithm actually invented a distance metric between two objects. So if I have two objects, which is I have the identity, that means I don't have any shape changes. And then I have another deformation fields, that means I do have shape changes. So for any two objects, that the LDDMM method basically define mathematically how to formulate the shortest path between these two deformations. And with the definition that we can basically mathematically compute the shortest path, the geodesic, from two objects. So you will understand how does the path or changing progress leading from one object to another. And this is typically formulated by the geodesic shooting equation. We called it as EPDIF. So the EPDIF is a partial differential equation which parameterized in the velocity space. So the velocity you can think of as tangent vector of the deformation fields, because the deformation is in the linear space. So the geodesic shooting equation basically tells you that starting from the original point, the source object, and then if you trying to solve this partial differential equation for the time-dependent tangent vector, the velocity field along the time, then you can always find a shortest path, which is the distance metric, shortest distance metric between the two objects. And then once you figure out what the velocity is, then you project it back to the transformation fields. So that's what we called entire LDDMM plus geodesic shooting. So I see some question probably in the chat there. But I apologize that I can't read Spanish. So feel free to speak up if you have any questions. I will constantly check. What framework? So for this entire thing that we used is based on the LDDMM algorithm. Okay, so it's a diffeomorphic image registration, and it's particularly solved for looking at the optimal transformations between two images and parameterized by diffeomorphisms. So that's the framework we are talking about today. Okay, so for our method to actually understand or to try to teach the neural network to understand the entire geodesic shooting, the path, one thing we want to emphasize is that because the geodesic shooting equation is very expensive, if you look at all the terms right there, you have to solve the partial differential equation with all the different terms. And if your image space is very large, particularly if you deal with medical images, 256 cube, that's the typical dimension, then solving this very expensive equation, it can be very time consuming, especially when you train networks. So for the current deep networks, for example, Voxmorph or whatever morph you have, they typically use stationary velocity field, which means that they don't actually solve this equation because they treat the velocity as a constant in the space. However, the problem with the stationary velocity is that it doesn't really, formulate the shortest path between the two objects. And in that way, when the distance metric is outside of the window, we can't really do statistical analysis in the deformation space. So my previous work basically identified that the velocity fields, the transformations are actually very smooth, the smooth signal. So if I gave one example with the velocity fields that defined on each image coordinates, it's a vector. But because the velocity is always smooth signal, so if you project that into a Fourier space, for those of you who are familiar with signal processing, is that for any smooth signal, when you parameterize in the Fourier space, actually it is always the low frequencies has good values or important values, and everywhere else is blank. That means the high frequencies doesn't have any values at all. So we basically project this entire geodesic shooting equation into this band limited space with a finite set of low frequencies, so that significantly reduce the dimension of having to compute geodesics. And we're going to use this into our neural network as well. So next, I'm going to talk about how do we design network to understand this equation. For those of you who are familiar with the neural operator, our idea is based on the neural operator. So since we have to solve such a expensive partial differential equation, the geodesic shooting equation, to understand the deformation process, so what we do is that we design a neural operator as a surrogate. So with any initial velocity conditions we have, that our neural network will be learning the function to directly output the solutions. So you don't have to numerically compute the very expensive integrators, the numerical operators of the geodesic shooting. So at IPME 2013, that my students basically presented the work that for this entire looking for the deformation process, the path along the time, so we can actually learn through a neural network. So we design this neural operator, the G theta, and what we do is that this neural operator, the network, should be able to take the initial condition that learned from a network from the image space, and then learn the entire geodesic function between each time point. So this G theta, the theta is the parameterized by the neural network. And then to do this, that we design a network G theta as the composition of the component. We first actually take the G theta. Remember that now we have everything. The network learns in the complex band limited Fourier space. So this is actually complex value. So if you see the mathematical value total there, that means it's complex value. And then we have the encoder, which means that after we take the signal, we project it to the high dimensional space. And then we have several layers of the fully connected network, trying to learn the mapping function between the time points. And the fully connected network will have two special operators. One is the W1, which is local transformation, which you can think of that it's an operator that extracts the local features of your input signal. And then H is the global convolutional signal, which means that we have a global operator that captures the global features of the input signal. So with the combination of the global and local feature, then every layer we are learning the mapping function between the time points velocity fields. And we also have to redesign all these network operators because we have a complex value in the Fourier space. So everything becomes complex valued operator and also complex activation function as well. So for all the details that please feel free to go back to the our IPME paper 23, so it's available online. And the entire neural operator, basically the composition of the encoder of the P, and then the iterative layer of the fully connected network. And also we have the Q, which is a decoder that projected back to the original space. So with all this design, every time point, the g theta, that will output the value based on the previous time points. And then we guide the solution to estimate this network by the real numerical solution of the geodesic shooting. So that's how we have the loss function there. And remember that the underlying data structure of the velocity is always smooth. And that basically gave us another constraint that the network output is also smooth. So that's why we have a smoothing operator in every activation function of the neural layer to guarantee the smoothness. And all this neural operator we designed here, then we put it into the context of the image registration. So giving the source and target images, and with the neural APDIF, that's what we designed, so we can output the deformations. And you can use this neural APDIF in optimization-based registration or deep learning-based registration. But the most important thing we want to show here is through the experiment results is that since we designed this neural network to understand the deformation process of how does one object to change to another. So if on the left side, we have the source and target, and then with our neural APDIF, we can directly predict how the changing process, the evolving process from one object to another. The current registration network basically tells you the final deformations, but it doesn't know the entire changing process. So we compared with the real numerical solution, which called Flash, and we can tell that the velocity fields or the evolution process is very similar with basically close to zero numerical integration error. And then we look at the different evaluation results on different resolutions, because since our network learned the entire geodesic shooting mapping function, so our network is resolution invariant. So if we train on smaller image dimension, for example, we have 64 square, and then we should be able to test on many different resolutions, because we are learning the mapping function instead of purely data fitting. And in this way, that we design the experiment and test on much higher resolution in the testing data set than the training. And you can tell that our method, neural APDIF, when we compare it with the numerical solution, we have really close estimation of the deformation process. And we also evaluated on the real data, which is the OASIS data set from the brain data set with 3D volumes, and we train on the much smaller resolution with 64 cube, and then we test on higher resolutions starting from 64 cube all the way to 192 cube. So our performance is very similar to the state of the art or the other current neural network. So for the DICE evaluation, that shows our network performance is close to the state of the art deep networks that does image registration. But we want to highlight that because our network is resolution invariant, so because we trained in a much lower deformation space, and then we show our time efficiency compared to the other current state of the art methods. So the last one, since I have the time limit, I want to show is about generalizability of the registration network. So if we put all this neural APDIF within the context of image registration, we find out that it actually increased the generalizability of the registration network. So our group are currently extensively validated the generalizability of the neural APDIF in the registration network. The initial results that we actually find out is that if we train the data set on the minutes data set, which is digits from 0 to 4, and we test on a completely different data set, which is the Google Draw that have different shapes other than digits, and then we compare with voxelmorph, lagomorph, or the existing registration research, that we find out our method actually has much better regularization on the deformation field. This means that our deformation turns out to be a lot smoother. This is all predicted deformation. It's nothing to do with the optimization based. And also we produce smaller error for the deformed image. That basically showed a very promising results of our method having a better generalizability. So I think that's all I have for my presentation today. And for all this neurorepeative, we have the publicized the code. So if you are interested, feel free to get it online. And also for the new IPS paper, integrating the shape feature and image intensity features to improve the image classifier is also there. Thank you.